Okay, the next presentation will be given by Dr. Xing-Ye Wang from the Changchun University of Science and Technology, China. The title of his presentation is Error Analysis in Deuterium Hydrogen Palladium Gas Loading System. Please, Dr. Wang.
Thank you, Chairman. Hello, everyone. It's a great honor to be here to participate in ICCF-23, and I'm very pleased to share my work and ideas with you. The title of my presentation is Error Analysis in Deuterium Hydrogen Palladium Gas Loading System. My presentation is made about 4 parts. One, a brief introduction of our previous work. 2, the chosen of calorimetry and the differences between them. 3, the error occurred in the systems. 4, some advices for reducing the errors. I would like to make a brief introduction of our previous work. Here is a schematic diagram of the gas loading system and the reaction chamber. In the reaction chamber, 2 and 4 are ceramic tubes, and 3 is the PD thermal wire for being triggered, and 5 is the heating wire. And the right one is a picture of gas loading system. We use isothermal method to calculate the excess heat power. The excess heat calculation is mainly based on this. K is the heat conversion coefficient, and the delta T is the change of the temperature, and the delta P is the input power. K0 is the value of K in the calibration experiment, and the delta T is the period of time that the experiment lasted. Here is the typical result at 90 kPa of deuterium. And the left figure is RTDs in the system of different positions, and the right is a fitting curve of input power and the K based on nitrogen deuterium at 90 kPa. From figure we can see that when the input power is above 200 watts, the KPD at the deuterium is becoming higher than KPD at the nitrogen. That means we can measure the excess heat power in the calorimeter. We measured about 90 watts of excess heat power at the input power of 415 watts. That's an obvious and exciting result. Here is we use the isothermal method to calculate the excess heat power. Consider the different thermal conductivities of the gases used into consideration. There would be a different temperature distribution and gradient in the reaction chamber. Consider this, the results obtained by the isothermal method might be not accurate, and is there any excess heat generated in the reaction chamber, and how much is it? Therefore, we introduced the heat flow calorimeter into the system. The left is the old apparatus used before, and we added the heat flow calorimeter to the old system. Here is a schematic diagram of the heat flow calorimeter, and the 9 is the reaction chamber. Compared with the old reaction chamber, it doesn't have the water circulating jacket, and the 10 is the aviation plugs for data convection and power supply, and 11 is HFC. And this is a picture of the calorimeter and the reaction chamber in the cavity. The dimension of the cavity is 17.6 cubic decimeter, and it has nearly 20,000 thermal cables in total. And then we calibrated the calorimeter with at 1 atm nitrogen. Here is the result. And this is the results from HFC. The left one is a triggering result at 90 kPa with different input power. And the right one is a triggering result at different pressures with 300 watts. We measured the largest excess heat power of 13.6 watts at 220 Pa at input power of 300 watts. In an ideal calorimeter, the heat release inside the calorimeter will be fully detected and measured. However, in actual situations, the calorimeter will always be unable to collect the internal heat completely. For example, sometimes the electric wires or gas inlet or pressure meter are connected to the reaction chamber through the calorimetry, causing part of the heat escaping out of the calorimeter before measurement. So we calibrated the calorimeter with 3 different types of gases as 1 atm, argon, nitrogen, and hydrogen. Here are the calibration equations, and this is the sample temperature in argon, nitrogen, and hydrogen calibration. We remove the PD sample and change it into inert materials. From the figure, we can see when we use nitrogen or argon for calibration, the sample temperature is higher than the hydrogen calibration. And the same situation with the aviation plug temperature. The aviation plugs is outside the calorimeter we use for data connecting, and when we use nitrogen or argon for calibration, its temperature is higher than hydrogen. That means there are more energy escaping out of the calorimeter. We compared the calibration equation of hydrogen and nitrogen respectively. There is a relationship between applied power and the signal of the HFC, respectively nitrogen and hydrogen in the calibration. It can be seen when the calorimeter needs to get the same signal, the required applied power in nitrogen calibration is higher than hydrogen calibration. Conversely, when we use hydrogen for experiments or deuterium for experiments, based on the nitrogen calibration, this differences of power will be misunderstood as the excess heat power. And this will subtract the calibration equation of hydrogen from the nitrogen and argon respectively. And this is the occurred error when using hydrogen for triggering experiments based on nitrogen and our argon calibration. From figure we can see, with the increase of the input power, the error increases too. Here is the excess power. Here is the results of excess power at 30 kPa deuterium with different applied power. Excess heat power increases with the increase of input power. Based on the nitrogen calibration, according to the analysis just mentioned, the error will also increases. And this is the results of excess heat power with 300 watts input power at different deuterium pressure. The heat transfer in the calorimeter and the calorimeter to the ambient environment is a complex combined convection and radiation heat transfer process. When the pressure in the reactor chamber is above 200 pounds, the convection heat transfer increases gradually. That means the reactor chamber has a better conduction to the ambient environment based on the nitrogen calibration. When the pressure is below 200 pounds to vacuum, radiation conducts the heat transfer. That means there will be a higher temperature distribution of gradients in the reactor chamber, and there should be more energy. Because of the temperature distribution, there will be more energy escaping from the calorimeter. We suppose there should be a critical a key pressure or key pressure range that it's the reaction chamber has the lowest thermal conductivity to the ambient environment. That is, the minimum energy escapes from the calorimeter before measurement. We would compare with the calibration. We would measure a largest excess heat power. That is to see, at the same time, the error is the largest. The key pressure we suppose it is relevant to the Condensed effect. When the molecule-free path of the gas is close to or larger than the dimension of the reactor chamber, the thermal conductivity of the gas decreases rapidly. We should also pay attention to the materials we use in the reactor chamber. We use the two aluminum oxide ceramic tubes. The ceramic has micropores in it and it also causes the Condensed effect. Here is the result of the calibration of the 30 kPa of hydrogen. And we did another round of experiments, and we adjusted the results from the results 90 kPa to 100 kPa with a calibration of 1 atm of hydrogen. Results 100 kPa to 90 kPa with a calibration of 30 kPa, and no obvious excess power measured. Here is a brief conclusion of this section. The critical cause of errors is that energy is escaping before measurement. This is mainly about 4 parts. The structure of the calorimeter. Energy escapes from gas inlets, aviation plugs, pressure meter, or other apparatus connected to the reaction chamber, and the thermal conductivity of gas type. Different types of gas has different temperature distribution, has different thermal conductivity, and when we do experiment, there should be different temperature distribution of gradients in the reaction chamber. Pressure and heat transfer patterns. Different pressures of gas has different thermal conductivity, as mentioned before. And also, the heat transfer process in the calorimeter is a combined convection and radiation heat transfer process. And we also should pay attention to the Condensed effect. The molecule free path is close to the dimension of the chamber or the materials we use in the reactor chamber. And here are some advices. Use heat flow calorimeter to measure excess heat power, and use same gas type for calibration and experiment. Use inert materials for calibration.
Notes and effect.
The same pressure used for calibration and experiment. And the last, try to avoid the condensing effect. Thank you for your attention. I will please to hear your question.
So, okay, there are a few minutes left, then we open discussion. Okay, here. So